covers it, but in that class, there's so much stuff that we have that we just don't have time. In fact, doing the meter certification is going to hurt us in that class. But it's neat. Well, we were going to do it, but we were told Mr. Perry's class was going to come down, but we can't do it now because they canceled these classes for a week. So it'll probably be next week when we do the meter certification.
So what they gonna do about the rest of these classes, like midterm too and all that?
I don't know. If we can't find anybody to substitute, they'll have to cancel. I mean, there's no other option. You got one or two options. Either you find somebody to do it or you cancel the classes. I don't know. I don't know. I have enough trouble keeping up with my schedule.
You got a lot.
This is what I'm working on a review, which is what normally this is where we'd start off with the actual class. Because by the time they take the troubleshooting class, they've already had most of the stuff they needed. So we start off with a review. What we'll do is just basically look at the sensors and some of the electrical components. These are some of the things we might want to sense, right? You might want to sense presence, distance, position, pressure, flow, light, sound, temperature. These are the main things that we sense. There's a lot of other things we can sense. We got humidity sensors, we got pH sensors, we got all different strength sensors, we got flaw detectors, we got all the types of sensors out there that you might run into. But these are the primary ones right here. Of course, sensors are either going to be digital analog, okay there, right? Understand. Even some analog sensors are used along with an A to D converter to make them appear to be digital. So we don't. But to sense presence, we use what we call a limit switch. This is an electromechanical switch. By the way, a limit switch is a proximity switch. But what has happened is limit switches were around long before electronics was even a dream. So what it's like when the first operating system that was on a disk was put out, it was called a disk-based operating system. Well, all versions of Windows is a disk-based operating system. So they're all loaded off a disk. But DOS is the first one, and then everybody else has a different name. So that's basically what's happened here. So limit switch has its own name. Even though it is a proximity switch, we call it a limit switch. So normally when we talk about proximity switches, we're talking about the non-contact version of the switch, even though they're all proximities. Of course, photoelectric, we know about those, right? Inductive, capacitive, reach switch, Hall effects, and ultrasonic. And this guy here has all of them on there. We don't have any temperature sensors up here. All these down here are non-contact, right? You understand? The non-contact flow, force and pressure, fluid, power, speed. We've already looked at tachometers and incremental encoders. And then the variable reluctance. We know what that is now. Are we okay there? Okay there? So that's one that was on the test. Position, we have potentiometers, which are analog devices. We have LVD keys, which is what the diagram on the show, and these are linear voltage differential transformers. And then we have our encoders. We have absolute and incremental. So the one on the test, even though it's a variable reluctance, would be considered to be an incremental encoder. So analog, we okay. Thermocouple. We'll look at these later on. These guys develop a voltage that is proportional to temperature. This would be analog. So it's going to vary. So analog, what advantage does the analog have over digital? So precision. I've had people that tell me that digital is more precise than analog, and that is false. I see this all over the place. Analog it gives us the ability to deal with infinity.
I would say this on my query on temperature sensors, pH sensors, and all that. I actually have to go in and calibrate them. Which on my temperature, I use 2 micrometers to take the reading there.
Usually what you usually do is you set what we call a span. I don't know if y'all know what a span is. So a scale, what we would do is we would zero it out, and then we'd put a certain amount of weight on there. And then we'd say, okay, this is 50,000 pounds. But when you put 50,000 pounds, it changed your zero. So we'd go back and redo our zero, and what you did is you calibrated between a range, and that's what you're doing. So you have a high temperature range, you probably calibrate, and a low temperature range. But these guys, thermocouples are linear devices. They're proportional devices. So what that means is they vary their temperature. They create a voltage. So what's nice about thermocouples is they don't have to be powered. You'll run into these in stoves. So you use thermocouples in your oven. They're that size. If you got a gas water heaters don't have a single wire hooked up to them, but yet they open and close valves with a thermocouple, because the thermocouple creates a voltage that will open the gas valve for you. The pilot light's lit. Of course, digital. What's nice about digital is the simplicity of the technology. So digital is easier to process. Get things in ones and zeros, truths and false. It's more precisely to transmit, to get it from point A to point B. Analog values are hard to maintain over distance because we lose some of them. But analog, we get a continuous varying output. A digital is going to move in steps, or going to give us pulses, right? Potentiometers, we okay there now? So y'all understand that? So what we do is we attach what we call the wiper is attached to whatever's in motion. And then when this moves, it moves the wiper proportionally around the resistor, and we get a voltage that's proportional to. You can't say it changes the resistance value. What it's doing is changing the ratio of resistance. And the next slide is good. This is a linear variable differential transformer. Then we'll look at its operation in a minute. It's really, really neat. But this is the resistor. This is what you're doing. So you're not changing the resistance between A and C. You're changing the ratio of the resistance between A and one reference, right? So notice what they're showing is I turn it this way, resistance R to B goes down. If I turn it this way, so they're very opposite of each other. So the only difference I know that makes a difference between which one you use as a common. So you're either going to use C as a common, or you're going to use A as a common. What that varies is which direction you turn the ball. So if you want it to increase when you turn it from left to right, or clockwise, you hook it one way. If you wanted it to decrease, you'd use the other as the common. Does that make sense? Because notice, these two sides vary what? Exactly opposite of each other. But they always have the same proportion. So the sum of these two resistors would always equal to the resistance between R and C. Y'all understand that? Yes or no? This is the one I was looking on YouTube. So this guy literally made an LDDT out of straw. So what they do is they take, so basically it's a transformer. So it's a straw. And what he's done is two different secondaries. Two different primaries. And they're wound opposite of each other. So if one of them, if he wound it clockwise, the other one he wounds it what? Counterclockwise. And what he does is he uses the center as the common, and then puts the two outsides. Y'all understand that? Pretty neat. So what happens is that then he's got the secondary is going to be on a straw that he's sliding in and out of this. I'm sorry, it's not a straw. He's putting a metal rod in here. So what the metal rod is doing, if it's exactly in the center, then both these guys would put out a signal, but they would be 180 degrees out of phase. So if we looked at this like a battery, let me get something I could draw. You got it. So what we're doing is we have two batteries that are facing toward each other. Now this is going to change. This is actually AC. And then what we're doing is we're measuring the voltage right here. Y'all understand? Now if this is a 5-volt battery and this is a 5-volt battery, what would our voltage measure? It measures 0. But what we're doing is we're changing the ratio. So it always equals. So let's say this goes up to 6, this goes down to 4. What's it going to measure now? Well, it's going to measure 2, but this side's going to be negative and this side's going to be positive. Right? You understand? If I come over and swap the polarity, if I make this 6 and make this 4, then now this side's going to be negative and this side's going to be positive. Y'all follow that? Yes or no? Yes or no?
So the
So the
lower one
larger
is
side
the-
is always going to be positive.
Yeah, because yeah, so it depends on where you're pushing the current through. So this guy here, this negative is going to override this by what? By 2 volts.
So why is it negative to negative and not negative to positive?
Because we don't want to hook them up to series 80, we want to hook them up to series opposing. We want the two to subtract from each other.
Oh.
Okay, you understand? So now, what I can do is if I'm changing this voltage, so let's say I come over here and both these are variable. And they're varying in opposite directions. And I have these mechanically connected and I have a little knob. And I'm pushing this back and forth. Well, if it's exactly in the center, I would get 0, right? You understand? But if I start moving in this direction, I would get a voltage, but it's either going to be minus or positive. It might be a minus 2 volts if I'm going one way, or it might be a positive 2 volts if I'm going the other. So now not only can we tell a position, but we can tell the direction of it. We can tell if it's going left or we can tell if it's going right from a 0 point, right? You understand? Yes or no? Well, that's exactly what an LAVT does, is it's got 2. So what I'm doing is I'm changing the core. So another thing that determines how much voltage we get is the strength of what we use as a core. But if the core is all the way on this one and it don't get on that one, then this guy's going to put out a lot of voltage. This guy over here is not going to put out a lot of voltage. Right? You understand? If I do that just opposite, then what's going to happen? If it's in the center, then the two are going to subtract from each other. We get 0 out. But then what's going to happen? Watch the thing. Here, so he's sliding the secondary, into there. That is secondary. And then watch what happens on his oscilloscope. So here's the output right there. See it change phases? Can you see it change phase? Sorry, here's it. Hit me. Well, he's got his scope looking at. Okay. So what he's able to do is not only to tell the position, but he also can tell the direction. These are used for LAVTs, so really use. I don't know what this is. High pressure gauge made. This is going to show y'all. So that might be real neat. I think I got some really fine gauge transformer wire in there. I thought that was so neat. And I actually make one of those things. They're pretty rugged. They're put inside, they're all sealed up, kind of like a piston on a car. You have 2 rods coming out of them. So they're really, really rugged. So everything's exposed, sealed in there, through seals. These are encoders. Are you okay with that? So this would be an incremental encoder. Used to sense not only position, but notice what they've got. They've got the photo cells offset. So what happens if this guy pulses first, then it means they're moving in this direction. If this guy pulses first, it means it's moving in that direction. So what we got, depending on which direction we're moving, is going to give us a pulse, but not only can we tell a count, but we can also tell a direction. So this is what the robots run over there. So the robots have counters, but we are going to go minus an zero or the other way, right? You understand that? This is an absolute encoder. An absolute encoder actually puts a code up here that indicates a position. You'll understand that. Now, what advantages an absolute encoder comes up is if we're at a certain position and we turn power off and everything stops, when we come back on, the absolute encoder gives us a position. An incremental encoder, we have to count that. So an incremental encoder, we have to feed it into a counter. And what happens when you lose power on the counter? You lose your count. So that's why all our batteries, that's why all our robots have batteries on, because they use incremental encoders, and they got counters in them. So if we lost power, we'd lose what zero was, right? And we wouldn't know which way to count from. So this is a pretty good animation that I found right here. And you can see this absolute encoder is actually giving us a count indicating its position, where an incremental encoder just gives us a bunch of pulses. That makes sense?
Yeah, because what I'm related to is on the carriers that I work on. They got what we call barcode readers. Apparently it's just an encoder. And it's in the places where they're actually putting parts on the doors. I've noticed that the barcode reader is just a series of lines. Exact same spacing and everything.
Well, then it's incremental.
And so I was wondering why they call it a barcode reader when it never even looks at barcode. And that makes perfect sense because it's counting bars as it goes to, lets it know where it's at
on that line. They can use that to decelerate, but the problem is it's got to find itself. So odds are you park it against a sensor so it knows where zero's at. It's just like your printers. A lot of your printers, especially inkjet printers, use incremental encoders. And so when you turn them on, you hear them do a reset. Or when you restart your computer, they do a reset. And what they'll have is they'll have like an optical interrupter over there. They come over and they find zero, and then they step out. And then from then on, it's all counted. That's all it is. But they have to find them. So incremental encoders are really neat because we can use these as, not only can we use them to sense position, we can also use them to sense speed. Because the faster the pulses are coming by, if we're going to use them to sense position, then we're going to have to sense direction. So we'll have to have the two like this, and you get a waveform out depending on the direction it moves. So that makes sense. Are we okay? This is, I don't know where I got this animation from. I got it off the internet.
I'm glad you did. That explains a lot.
But the problem with this is absolute encoders, we're limited to one revolution. Unless we have something where we pulse and increment up by one, right? You understand that? Incremental encoders don't make any difference because your increment, what determines how far you can go with incremental encoders is determined by how big your counters are. You know.
So absolutely, would that be used to measure like distance?
Could an incremental encoder could be used to measure distance too, because your vanes are going to be a certain distance apart. So every time this thing here pulses, it would indicate a certain distance of motion. Now, if you ran this through like a gear or something like that, you'd have to complement. You'd have to do that, and that's when I showed y'all the incremental encoders that were on the back of that motor. I showed y'all that, and there was only like 3 of them, but it compensated by going through a gearbox, right? You understand? So it did a torque multiplier.
The reason I asked, we use encoders that have like piano wire attached to it, and it's got a set point. The main machine that I'm thinking about is using a carrier that actually carries the car around weekends and different stations it goes to, but it's so precise to the movement. And like when it drops down, it will go until it's been 3 millimeters. I think it's got power for 6 millimeters.
Yeah, well, that would be no big deal with an incremental encoder or even an absolute encoder. It wouldn't make any difference. But this, like I said, here you have to have a circuit that counts. So that means you're going to have to start counting from somewhere. So some way you got to have some way that you can reset that count. So that
these are sealed, I never seen the inside of them, so I have no
well, there's
idea.
some way they got to say if it's got an absolute encoder on it, then you don't have it's got a 0 on it. So that means it would always have the same count at a certain position. So it might have, so down here it might have a count of 15, which would represent so many millimeters, but you don't have to worry about setting 0. And if the line stops or the power fails, you fire that sucker up and it's still there. You don't lose the count. So it would probably be an absolute encoder on that, or a battery backup. What they called it in a robot is kind of a misnomer or misnomenclature. They called it an absolute encoder, but they called it a battery backed up absolute encoder because the controller sees it as an absolute controller. It don't know the counters are out there. So it might be that. It might have batteries on it.
I'm pretty sure it's got batteries.
Well, then that is probably incremental.
And if the boxes ever go bad, we'll change the box and it'll be exactly what.
Okay, on those different types of photoelectric sensors. So we have diffuse, which actually bounces light off the logic. We have a retroreflective, which bounces off a reflector in the object that it senses, moves, breaks the beam. And then we have a through the beam, which one has the ability to have the longest distance? Through the beam. Because these guys got to bounce off and come back, right? You understand? So through the beam has the ability to have the longest distance.
Would a retroreflective through the beam be somewhat the same thing?
Well, yes and no. On a retroreflective, your transmitter and receiver, and they work on the same principle of breaking a beam. But they work on the principle of, these guys work on the principle of reflection. This guy don't work on the principle of reflection. That makes sense? Now this, the transmitter and receiver are inside one unit. Here it would require 2 units. So through the beam would be a little more expensive than the other two. This one has this one depends on the device to have some reflection. So on the Festo line, we actually use some of them, and we adjust the sensitivity. Y'all understand that term now? We adjust the sensitivity not to see black. So that means now the robot can tell if it's working on a black cylinder or if it's working on a red or a reflect. And then that way it knows which piston to pick up and put in there. And you'll see it swing around and drop down and put its diffuse sensor on the side. And that's what it's doing.
Some I've always been doing robots down there. Most of them have a blue light. Ones that actually detect openings or something. Some have blue lights and some have red lights.
I don't know the features of it. I don't know. That's a good question. I don't know. It might be the surface that they're trying to reflect off of. And that's the only difference I would know.
But I know when the robot fits the windshield, it's got a blue thing. They like to go all 4 corners.
Yeah, but it's probably looking for the black that's on the seal. So it might be that blue reflects off black better than red does. I don't know. It's a good question. We might,
Yeah, I think it's the intensity too also. I think red is the highest.
I don't know. Yeah.
I just know some robots have blue sensor lights.
I just remember when we used to do 3D before they came up with the polarized lens. You had one blue and one red. But that's a good question. Temperature devices, we have thermistors. Thermistors are solid state, they're semiconductors. We can get what we call a negative temperature coefficient or positive temperature. So a thermistor varies its resistance with temperature. Did I put that on there? Yeah. These are non-linear devices. They have an exponential curve. So normally we use this over very narrow temperature ranges. So these guys are used if you have a digital thermostat in your house. These guys, that's what's in there. But you think about it, a digital thermostat, you only vary over a very small range. So a thermistor, so thermistors are used all over the place. They're really cheap. You can get them all sizes. You can get negative temperature negative, which means their resistance goes down as temperature goes up, or you can get positive temperature compensated, which means their resistance goes up as temperature goes up. Of course, we're going to have to use these with a Wheatstone bridge, right? Or we're going to have to use them with an external resistor. These guys are going to have to be powered up. Thermocouples. Thermocouples are real neat, and they produce a voltage that's proportional to temperature. They're not extremely accurate, but they're accurate enough. You'll run into these all the time. We don't have to power these things up. They create a voltage that's proportional to temperature. How they do it is another thing. They are very sensitive in that you've got to maintain, they work on the principle of dissimilar metals, and you can look up the chart. So the temperature range depends on the two metals you do, and you have to maintain those metals all the way back to the instrument. So you cannot splice these things, you cannot put different wire in there. We had these thermocouples on our jet engines on the planes I worked on in the Navy, and the thermocouples went all the way around the whole jet engine. It was a turbine inlet temperature, and we had a wire break out there. What did we do? We went out there and soldered it back on there. We didn't know. We did a good job, and it didn't work. So they had to fly the plane all the way back to Lockheed. It was a Lockheed P3, and they had to replace the whole thermocouple harness on that plane, which is pretty interesting. No, you can't mix regular solder with. What's that? I don't remember. If you remember that, you're good. I just remember the indicators had a red line on it.
Now you could do the props.
So you're familiar with the P3?
130.
Same thing. One of them's over the wing, one of them's under the wing. They both ran the same engines.
Props. I had to solve the prop.
Yeah, but those weren't thermocouples. Those were brushes.
No, I'm talking about on the prop itself.
We didn't have a thermocouple on front. It was brushes because they ran heaters. Yeah, we had to solder those all the time.
This is the wiring inside the back.
Yeah, that was the heaters that went down the strip. We got in trouble. We got in trouble one time. We had one of the little heat strips that run down the prop, and we were in south of nowhere. We was down in Diego Garcia. A little piece of wire started coming out, and that was the defroster for the props. And because we could get the P3 could fly up around 35,000 feet, and so they had to heat the props and everything, and the leading edge of the props so they'd ice up. And we couldn't fly the plane, so the pilot came out there and grabbed it and pulled that strip all the way off that engine. So we flew all the way from Diego Garcia back without heat on one of our props. And we didn't fly at 35,000 feet. We got in a little trouble about that. But they got over it. At least we made it home. I didn't know you worked on P3. That's a good plane. Phasing it out too for total jets. So P3s are turboprops. But yeah, these guys are a little more complicated in that you got to maintain this metal all the way back into the sensor. By the way, these guys are very popular. I should have brought one in. A lot of your meters now come with little thermocouples that your meters can measure, and they'll tell you the metals that they use. RDTs, these are very popular. If you've got a water heater out in your house, it probably uses an RDT. If it's electric, we know that resistance varies with temperature. The resistance of a wire varies with temperature. These guys are kind of opposite of most devices. On wires, their temperature goes up their resistance goes up if temperature goes up. which means it's really neat and they're really, really accurate too. So we're seeing RDTs replacing thermocouples on temperatures below 600 degrees. Usually above 600 degrees is still dominated by thermocouples.
We're talking about when we use
They have, it depends, but Cromel, Anumel, is one of them. We could look up and it's a chart, but what they do is they change it depending on the temperature range. So we can get these all the way from, I've got a chart. I think I've got it in, one of my classes. I'd have to find it. It's probably just as easy to look on, and they call them types, by the way. And then they have a color code. And then we'll look at images, and this will probably be the best way to see the chart. Yeah. So here's your chart right here. And they have a color code for the different wires. This doesn't give us a temperature range on here. But so copper constantine, composition, iron constantine, Cromel. So and then they have a different color code. I was trying to see if they showed one that actually showed their temperature range. I think this one does. Now this one, of course, is in centigrade. If it pops up. Of course, it's not going to give me the picture. It's going to give me the sites that sell them. All right. But you can see this guy right here, which is they give us the metals.
You can do view image and
I don't know. I'll try. Oh, there we go. Thank you. This doesn't give us the metals though. This doesn't give us. Yeah, it gives us an abbreviation for the metals. This gives us a color code. But see, these guys go all the way up to 200 degrees centigrade just on this chart right here. And I don't see the code for the metals, but what the problem is you have to maintain. And Japanese uses the different colors than we do, and this is the international color. So,
Japanese, everything's red and white.
red, white, and blue.
so we could probably find it. I've got a better chart somewhere. I'll put it up there online. Like I said, these guys are still using them all over. In fact, to make sure the temperature of the steel was right, they would actually take a big old long pole and put a thermocouple on the end and dip it down in there and pull it back up and throw it away. But, that's the way they measure to make sure the temperature of the steel.
I remember a guy, he actually, every time they do it, he'd take that little sliver of metal, whatever it was, and put it in the jar.
Oh, really?
And he took it home and ended up firing it for steel.
Oh, really?
Yeah, somebody said people sell them to recycle.
Infrared is becoming very popular. The only problem with infrared is that, so what we're doing, infrared actually measures wavelength coming off, and they can measure the percent of the wavelength. Heat sends out infrared, which is light we can't see. And if they can measure that, then they can calculate the temperature. Problem with this, of course, these have got to be electronic. They got to be externally. And you say these are becoming very popular because now all you ought to do is just point it at it. But the problem we have here, a lot of them use a laser pointer on. And why is that? So you know exactly what you're measuring because they'll pick up background. So if you're off a little bit over here, then you're going to be measuring this, right? You understand? You're not going to be measuring the actual part of the lawn. So a lot of your handheld laser, infrared. It's not the infrared that's measuring the temperature. I mean, it's not the laser that's measuring the temperature. You're using the laser to aim the thing, right? That makes sense. Are we okay? Everybody okay on solenoid? So solenoids are electrically actuated linear actuators, right? So they turn power source into a linear motion. And then, of course, we take a solenoid and attach context to it, and we create a relay. Are you okay there? These are pretty neat. These are single acting and double acting cylinders. That's pretty neat animation. So single acting cylinders, we use force to push it one direction. We use pressure to push it and somebody else brings it back. This is a 3-position valve, by the way. So, and we don't cover that very much. This guy would have what they call a closed center. So notice when it's in the center, fluid don't go either direction. See that? And then we shift it. Huh?
Just back to tank.
Now this is actually for hydraulics. Normally on pneumatics, this would have a symbol of a little arrow pointing out. But in hydraulics, this is the symbol for the tank. This would be the fluid returning. So that's one of the major advantages. Pneumatic systems are so much cheaper because, one, you don't have to run all that piping to get it back after it's being used to get it back to the water, to get it back to the tank. Another advantage, of course, is the low pressure application. You use very low pressure, which means the tubing can be plastic. A lot of times, the tubing can be plastic. The highest pressure I've ever seen for pneumatics is 600 psi. That's the highest. And they really had to take care of that air because they had to chill it and get rid of the moisture. Because what happens is that water holds air, but it only holds air for so much cubic feet. If you decrease the amount of cubic feet when you pressurize it, what does the air do? Well, the air don't compress. Liquids don't compress. So it just comes out because the air can't hold it. So if we deal with compressed air, we got to do something about that water. Because as soon as we compress it, it's going to release that water, right? You understand? So we got to remove it. Now, this compressor right here is really neat. I don't know exactly what they're using, but to remove water. Most house compressors, you drain them all the time. Make sure you do that because if you don't, the tank's going to rust out on the inside and sooner or later it's going to blow up.
Yep.
Electric motors. This is where we've done very poor on right here. We have DC, electric motors are in 2 different categories. We have DC and AC. DC, we have shunt, series, and compound. We have stepper motors and brushless motors. We got basic introduction to stepper motors, right? AC motors, we have single phase and 3-phase. And then we have synchronous motors. We have single phase, synchronous motors, and single phase, 3-phase. Are we okay? Now this is a DC motor. DC motor consists of several components. We have a field, which is stationary. Some people refer to this as a stator, but that's not exactly true. But you got to be. It's like when you go to work, you might learn a certain terminology that might be different than the place you go. But what you have to do, you need to teach the language of the place that you go to, right? And the terms they use might not actually be correct, but it's the terms they use. And that's the language you got to speak.
I know the language.
Of the place you work. Yeah. Now, the actual true name of the field that's stationary, y'all have to understand, all motors operate on the principle of repulsion and retraction of magnetic fields. One of them's got to be moving. The other one could be stationary or whatever. Okay. So DC, the ones that's moving, is called the field. And this can be a permanent magnet or it can be an electromagnet. The one that's stationary, we refer to that as the armature. That's the technical term. Some people will call the stationary part the stator for the stationary part. And they'll call the rotating part the rotor. That's what we call them in an AC. Don't understand that. Now what we have to do is we have to make one of these fields rotate. But what we do is we literally let the motor create a rotating field. So when the motor starts spinning, it constantly switches the direction on the current going into the armature, which causes the motor to rotate. And so this switch assembly back here, this is called the commutator. Can y'all see it has segments? And what it does is the brushes never move. But what we do is we always keep a north on this south and a south on this side, and then they always reflect against the opposite pole. Does that make sense? And the motor does what? it spins. So one side is repelling, one side is always repelling, one side is always attracting, unless we do what? Unless we change the current in the armature. And then they switch positions and the motor would do what? Change direction. By the way, we can change the polarity of the field. Two ways we can reverse it. We can change the polarity of the field, or we can change the polarity of the current going through the armature. Normal practice is to change the armature. And we leave the field alone for reasons we don't talk about. So the armature will always be electromagnetic. But the field can also be a what? A permanent magnet. So we have permanent magnet motors right here. Commutator is slotted copper ring used to transfer current from the source to the armature. The slots mechanically change the direction of the current in the armature, causing the motor to evolve. Rotate. Now, how are we going to get electric current to the armature? Well, what we're going to have is we're going to have these things called brushes. These are carbon. And what these carbon do is they transfer the energy to the commutator. Carbon brushes with copper wires attached used to transfer current from the power source to the commutator. And we normally reverse these things by doing what?
And the field of
Normally. No. We normally reverse them by changing the polarity of the voltage applied to the armature. We can reverse them two ways, but this is the way we do it. So that means all DC motors, whether they're series, or whether they're series, shunt, we change them the same direction. Also, some of your motors, shunt motors, if you remove the field, they'll run away. So we don't want to take a chance of breaking the field when the motor's running. A series motor will stop. Shunt motor can run away. We're not going to get into the why. It don't make much sense. But if you understand how DC motors work, and you'll get those in motor controls, then you'll understand why a shunt motor will run away.
I have an off-subject question. What causes, like, when you put something in a microwave and it spin one way, and then you put something else in there, it go the opposite way? Why?
It's just a regular little series motor that it's a series motor that just does that. It uses a weird tendency. And you're right. I mean, it reverses direction, but it's the type of motor they're using. And they don't do it on your reason. It's just the type of motor. Which is really interesting. I'll try to show you.
I used to always stand in the microwave in front of it and wonder why it does it.
It's not electronic. It's just the motor that they use, depending on which direction it was running before. The second time you do it, it runs out. This is what we call a shunt motor. We have two types. We call it a shunt motor, separate excited. Where I got this, they called it a common source shunt motor. Now, what we need to know about the motor is why we have different motors. Why we have a shunt motor, it gives us really good watt. Where's this? Gives us real good watt. Yeah, these guys here regulate speed. Yeah, really good. So we can vary over its range. We can vary its load, and it maintains really, really good speed. But it has okay starting torque. So it's not extremely high, but it's okay. Separately excited, what's really neat. So what happens, and it's really weird, guys, what happens on the shunt field, if we increase the current through the shunt field, the motor slows down but creates more torque. If we decrease the voltage on the motors on the field, the motor speeds up but creates less torque. So the advantage of a separately excited motor is that we can use the field to control the torque. Does that make sense? Now on the armature, if we increase the voltage, we increase the speed. If we decrease the voltage, we decrease the speed. So if we change the voltage of the armature, it varies in the same direction. If we change the voltage in the field, it moves in the opposite direction. So that's why if it opens, you're decreasing the strength of the field, the motor's going to try to do what? It's going to try to run away. So a separately excited motor, not only can we control the speed, but we can also control the what? Torque. Another advantage of the separate excited is if you're going to shut the mill down for a year, you can leave the field voltage on and the motors won't rust on. They won't collect motor. And that's, they did that at US Steel. So most of the DC motors at US Steel are separate excited. If they ever shut the plant down for a long time, if you just leave a motor stationary, it'll rust on it. It will. And then that rust is on all your pole pieces and on your rotor. I mean, those things are hard to break loose. So what they do is they just leave field voltage on. But they use these things all the time. They'd have one drive running the field and one drive running the motor. And you could basically have these things create the same torque over the whole range of motors. So this is one that preferred that. Now the other motor we have, of course, is a permanent magnet motor. These are usually used for fractional horsepower motors. DC motors, good gracious, you can get these things any horsepower you want. DC motors are very expensive because, especially these guys, because you have two electromagnets. You have the electromagnet that's in the armature, right? You understand that. And you have the electromagnet that's out here on the field. So these guys here take a lot of wire. And wire costs money. Another problem we have with DC brushes is these guys right here. These are brushes. And what happens to brushes? They wear out. So then and also you'll start getting goop in your segments. So DC, your segments between your commentators, so you got to maintain these guys. And you can tell these guys that they don't get maintained. Y'all can actually look in and see this, by the way. You can see the brushes down in there. Touching, you can see the commutator if you turn the motor. Huh?
Pushing my chair.
But the biggest advantage of DC is, the biggest advantage that DC had for so many years was that we could control these motors precisely. These separately excited motors, we could change the torque by increasing the field. And that would try to make the motor slow down, but what we do is we'd increase the armature. What we would get is we'd get the same speed at higher torque, right? You understand? So we could control the torque and we could control the speed. A regular shunt motor, we couldn't do that. And by the way, the normal way to reverse these is to reverse the what? The armature. Permanent magnet motor, the only way you can reverse this is to reverse armature. These are fractional horsepower motors, very cheap, very reliable. So just about all the motors in your car that runs all your fans and everything in your car is probably a permanent magnet motor. Runs your windshield wipers is a permanent magnet motor. But it's not the one that starts your car. So all the little motors over here on both the Festo line and the Amoco line are what? Permanent magnet motors. You get out in the industry, these guys are going to be very small applications. These guys that's running rollers and stuff like that, they're going to be big on DC motors. Probably compound motors. This is a series motor, this guy here. So the current that's going through the armature is the current that's going through the field. If we increase the current in the armature, in the field, we create more torque. The less resistance the armature has, so actually what we're doing is we're kind of changing the resistance of the armature. So when the armature is sitting still, it's got almost no resistance at all, just the resistance of the wire. When the thing starts spinning, it uses what we call counter EMF to make the armature have more resistance. So what happens is that if speed goes up, the available torque goes down. Okay, y'all understand that? A series motor, if it's stopped right here, the armature has almost no resistance. You put current on that, you're going to have maximum current through the field, you're going to have maximum current through the armature, you're going to create maximum torque.
You need torque to get started.
You get started, right. But the problem is, if you load them down, they're going to slow down to create the torque, because that's what you got to do. You got to get more field current, right? You understand? So these guys here are very poor for speed regulation, but these guys can create some torque. Your starter motor on your car is a series motor. Your hand drill has a series motor. So, and you know them suckers, they start slowing down. They run pretty fast, and you hit something, they slow down, but they slow down so they create more torque. So anything I'm not worried about speed, I just need a lot of starting torque and a lot of running torque, then I'm going to use a series motor. But the problem is they have very poor speed characteristics. Yeah, as soon as you load these things down, they're going to slow down. As soon as you let them go, they're going to. By the way, you never run a series motor unloaded, because if you do, it will run away. So we don't use these things on belt drives. We normally don't even use them on chain drives. We use them on gear drives, because if the chain breaks, these guys will run. If they run them unloaded. We use these guys on vacuum cleaners. Some small fans use them. By the way, this guy right here has so few turns that it has a very low. The problem we have with trying to run a DC motor on AC is something called X sub L, which is 1/2πfL. And of course, L's are made by nothing but coils of wire. And what this does is this creates an opposition in ohms. So what happens if frequency goes up, then the opposition of the motor goes up. They'll follow this. Okay. But if I can make L real small, then that means we can put frequency on a low frequency on this thing, like 60 hertz, and we can run these guys on AC. So a lot of people refer to these as universal motors. So we can run them on AC, but it's got to be low frequency AC, like 60 cycles, right? So this is why your vacuum cleaners will have these guys in there. Your AC hand drills will have them in there. But you could run that thing off AC too, but not 120 volts AC, because you burned it up, right? Because you put too much voltage. This is what US Steel ran. They ran compound motors. So compound motors has a series field and it has a shunt field. And so what we get is we get good speed regulation, but it's not as good as a shunt motor. And we get good starting torque, but it's not as good as a series motor. So these are compound motors. But these guys will run off electronic drives, and it took care of that. So this is predominantly DC motors at US Steel with these guys. Are we okay? They can be cumulative compound or they can be differential compound. Cumulative compound means that the series field is wired in the same direction as the field, as the shunt field. Differential compound means the series field is wired in the opposite direction. So a cumulative compound has a higher starting torque, but not as good a speed. A differential has a good speed, but not as good starting. So it all depends on the application, which type of DC motor you use. So guys, that's all the DC motors. So we have what? We have a shunt. Are you okay on the characteristics there? We have a permanent magnet. You okay there? We have a series. You okay there? And then a separately excited. I'm sorry, a compound, which is a combination of a what? Series and a shunt. Are we okay? We'll have to show y'all this. There's a method. For years, we drove. We varied the speed. We can vary the speed of the. Normally, we vary the speed with the armature motor. We vary the torque with the field. We vary the speed with the armature. So what we use is we use a silicon control rectifier. And what we did on a silicon control rectifier is that we would take DC like this, coming in, and then we would fire the SCR at a certain angle, and we'd get part of the cycle out. And of course, what would happen is the DC motor would average this out. Does that make sense? Now the problem is that it took quite a bit of electronics to figure out what we call the firing angle, because the firing angle would determine the speed of the motor. And this had nothing to do with digital. These guys were totally analog circuits. Well, what we'd like to do is we'd like to be able to control the speed with a what? You okay, Larry? With digital. So we got another technique that they refer to as pulse width modulation. Well, what we do is we don't change the frequency. So if you look at this point right here, of course, when I write on it, it's going to stop. By the way, I know we probably need to take a break here. I don't know how long we've been going. Really? So notice when we look here, this never changes. Oh, wrong side, Rich. This never changes. So if the time changes, then what's not changing is not changing the frequency. Y'all understand that?
Time's changing, the frequency's not changing?
No, time's not changing.
Oh,
If I said that, I'm extremely sorry. What's changing is, okay, so I chose the wrong side. So look at this. This is not changing, right? You understand? And this is not changing.
I understand.
so you're leading,
Yeah, I know. I drew it wrong.
leading edge.
Well, leading and trailing is a relative term. I just chose the wrong side a while ago. So what I need to do is I need to put the rising edge right here and the rising edge right there. Okay, so let's go ahead and notice those never change. So if those never change, then the time never changes. If the time never changes, then the frequency never changes. Right, you understand? So what's changing? The time that is high, right? You understand that? Well, what happens is your DC motor, and this is showing you the DC average right here. The DC average varies with how long it's high. So the closer we move to the entire period, which means then the more voltage we get it, and as we move down, the more we get, right? You understand? So this is a technique called pulse width modulation. So we're not changing the frequency, we're changing the width of the pulse. And we apply this to a DC motor, and the DC motor don't see this, the DC motor sees that. That makes sense? So what we're doing is we're changing and now we can do this digital. Computers love this. The 1100 PLC that we got has a pulse width modulation output on it. So we could use the PLC to control the speed of the motor. Of course, we would probably have to run it through some type of amplifier if the motor was big, but it has a pulse width modulation out.
What's the command that does that?
Well, all we do is we give it a command to change what we call the duty cycle. The duty cycle is the percent of the time or the period that it's high. So if we have a 50% duty cycle, then what would happen is the off time and the on time would be exactly the same. Well, if I tell it to generate a 25% duty cycle, then what that means is we don't change the frequency, but the off time would be longer than the on time, and the motor would run slower. But we're going to do this at a pretty high frequency. We don't want the motor to sing to us, and we want it to be real smooth. So these guys are usually a pretty high frequency. We're talking about 20 kilohertz or something like that would be the frequency, and then what they do, they change the duty cycle. And this is the predominant method now of controlling DC motors, the speed of DC motors, because we can do this digitally. We can do this with a PLC. We can do this digitally, right? You understand? Instead of analog, which is the old SCR drive. So this is a really neat feature. We already know what a stepper motor does, right? You understand this guy? What's what it does? So we have a permanent magnet rotor, and what do? Is we just switch the field. Can you see what they're doing? And each time they switch it, what's it cause it to do? Makes a step. We have what we call the slew rate. This is when we switch the field so fast, the motor looks like it's running continuously. If you exceed that slew rate, the motor will start jumping. So that's pretty critical. And what's nice about these is we can run them open loop, right? Which means what? All we do is tell it to move a certain amount of steps. By the way, the stepping motor we have over there, I'm doing a little research. It is a programmable stepping motor. So you literally run an application and you hook it up to a USB port and you tell it for each command how many steps to move. So the PLC all the PLC has says go to the next place, and then the controller inside the stepper motor moves it according to the program you put in.
Would you use that as a code?
No, because we're positioning it. I don't know. We'd have to look at that. We might could. It's because it's the way it's wired on the outside. You'd have to take it apart. It depends on how it's wired. Normally, so this is a stepping motor right here, and you can actually feel it lock into the steps. So when you turn it, you can feel it. So what we have here is this is the common right here, and then these are the other wires that run the steps.
Well, in a sense, you could.
Well, you could, but what you have is
steps.
Yeah, you'd have to come in and you'd have to tear it apart. But what the problem is the stepping motor probably has the encoder would have almost a 0 horsepower rating, and this guy right here would cost a lot of money. So I don't know. I mean, if I was a hobbyist, I might figure out how to do that. But if I'm in the industry, odds are you're never going to see that. I've never seen it. By the way, this is we can hook this up with unipolar or bipolar. Well, we don't have time to talk about that, but that's why it has a lot more wires, depending on how you run the motor. Unipolar is easier to control because what you do on it, unipolar, what you do is you connect a common to one side and you only put voltage on one side. So all you're doing with that is pushing it. A bipolar, you put power on both poles. So this would be an example of a unipolar. A bipolar, you put power on two sides, and what those guys do is those get a lot more torque. So, but it's harder to. Well, on both sides. So a unipolar, you put voltage on one side of the coil, and you put like ground or common on the other. A bipolar, you put plus on one side, and you put minus on the coil that was 180 degrees out. So on a unipolar, on a bipolar, you're pushing and pulling on both sides of the rope. On a unipolar, you're pushing and pulling on one side.
These are one direction as well.
No, they're not. All you have to do is change. You have to reverse the sequence. So these guys, we would be in trouble if they was bidirectional. That means I could only print in one direction on my printer. So what they're doing is they're changing the rotation of the field. Does that make sense? So if I'm making them go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, and then I go 4, 2, 3, 1, 4, 2, 3, 1, then what would happen? It would reverse. So yeah, we change it. These guys are electronically controlled though.
Well, in a sense, you could use it as an encoder, just count the steps.
You could, it's just that it would be more expensive and you couldn't use it for anything else.
I mean, could you not just count your steps you send to it, keep up with that?
Well, that's not an encoder. That's keeping up. An encoder is a closed loop system. And this is open loop, and that's what you're talking about, and that's the advantage of a stepping motor. They're very accurate depending on the steps. So these guys have so many steps. So if they had 40 steps around the rotor, that means each step would be worth 1/40th of a revolution. Y'all understand that? So you're right, we're not using it as an encoder, we're using it open loop. So an encoder is a sensor that I tell it to go so far, and then I use the encoder to see if it went that far. A stepping motor, we start it from an origin position, right? You understand? And then we just do what? Then we count steps. And each step would be equal to a certain amount. But we could spin it, and it would induce a voltage into these coils, but I just don't know how much. And which one we would use. This is a brushless DC motor. I'm fixing to go. I know we know. These are what we use in disk drives and stuff inside your computer. Every motor in your computer is a brushless DC motor. So if you got a fan motor, the fan motor in here is a brushless DC motor. The hard drive in this thing uses the brushless DC motor. Well, what they do, it kind of works like a stepping motor. But what they do is they switch this thing. They switch the field electronically, and the rotor is actually on the outside of the motor. And it's a rotating magnet. Now, what advantage does this have over a regular DC motor?
No brushes.
No electromagnetic interference. So,
You go all solid state.
what's that?
All solid state. No moving parts anywhere in it.
Well, you got your rotor. It's not solid state.
This one's hot.
Yeah, but you're using solid state. You're not using hard.
Right. It's only 10 seconds to 56.
Yeah.
Yeah. Hard drive.
Well, it's not even a hard drive.
Yeah.
It's solid state. You're using EEPROM. Same technology that you use on little thumb drives. Y'all see how this guy works? Y'all see how this works? So we use these guys in applications. They're fractional horsepower motors, but we're electromagnetic interference. I'll take this over. Next class, we'll go over and look at these guys. And we'll put a scope on these guys. So what I'll do is I'll fire up the DC source, and I'll put an oscilloscope on here, and you can see the noise these guys here generate.
So will the oscilloscope pick up the steps? How does that?
I don't know what you mean.
Uh,
If we couldn't look at all the steps, but we could look across here. So every time this thing here pulses, then that would give us a step, right? You understand?
Right.
This is a unipolar. So notice all they're doing is switching one side. So they got power up here, and then they're switching common. Now, these things are nice. They're real easy to electronic control. If this was bipolar, we would have to have 8 transistors. One of them would turn on the negative. The other one would do what? Would turn on a positive. But the advantage of a bipolar is that you can do what? You get more torque. Why we have so many wires out of this guy is that this guy right here could be wired either way. So you can wire this as unipolar, or you can wire this as bipolar. Which is pretty good. But here's your two commons. So if I was going to wire this as unipolar, I would do what? I would just tell them to take these two brown wires and hook them together, and then I would pulse these. Then it would move in steps. And you gotta know the right sequence. So you can't pulse this one and then this one, right? You have to pulse them one after the other like that. So we would have to look this up. We had a circuit. We'll look at. We'll finish this up. We need to talk about the AC motors, and then that'll be about it. So what we're gonna do next class?
We're gonna look
From the lab.
Well,
at the DC motor.
I know.
what do y'all want to do? We're either gonna do soldering or we can do a lab. What do y'all want to do?
I'm interested in solving.
You want to burn up?
Why are you
I'm interested
Why are you voting?
because we got to live many times. We need to solve the wires.
Yeah, rope wires. Soldering is a lot more mechanically sound. We had in our airplanes, in our P3s, they were changing the main display that pilots look at to figure out where all the sound was at. And they came out with a new version. What those ATs did, they came out, and it must have had, good gracious, 100 wires coming in the back of it. They came in there, and instead of redoing all the plugs and everything, they cut all the wires, put the new one in there, and used these mechanical splices to splice all the wires. And it was a mess, because these things took up a lot of space. And they had problems with that thing because, I mean, we're talking about very sensitive equipment. So anytime you're going to splice a wire, the best method is to solder. That's the best. That's the more reliable. more convenient is to use the mechanical splice. Mechanical splices, you crimp them on there, and it all depends on you get the crimp exactly right. So yeah, that's a true story. And that was a mess when you pull those things out.